For as long as we have built anything, we have built with wood. 10,000 years of houses, bridges, ships, and temples, and nearly all of it started its life as a tree. But right now, in China, engineers are raising 7-story towers and laying down bridges strong enough for fully loaded trucks, and they are doing it with a material that grows back in under 10 years. A material the construction world once sneered at as fit only for huts. A material that was never a tree in the first place. It bends instead of snapping. It traps carbon inside itself instead of pumping it into the sky. And it can already carry a vehicle across a river. That sounds impossible. It is happening today, in 2026. If you enjoy stories where a quiet breakthrough rewrites an entire industry while the rest of the world is looking the other way, hit the like button and subscribe. It genuinely helps this channel keep going. Because this is not a garden pavilion or a lab experiment. It is real buildings, real bridges, and a national plan already worth tens of billions of dollars. And the strangest part of the whole thing is this. The science behind it was finished and sitting in a Chinese laboratory back in 1987, and for almost 40 years, hardly anyone paid it any attention. Let us get into it. Start with the reason any of this matters because it is easy to miss. The modern world is built out of 3 things: wood, steel, and concrete. Each one has a fatal catch. Wood is beautiful and it is renewable, but it is painfully slow. A tree strong enough to frame a building takes somewhere between 25 and 75 years to grow. Think about that timeline. A sapling planted the day you were born might not be construction grade until you are middle-aged. Cities are expanding faster than any forest can refill, so builders reach for the 2 materials that never make you wait: steel and concrete. And that is where the bill comes due. Making cement, the glue inside concrete, releases carbon dioxide as a direct chemical reaction. You have to cook limestone at around 1400 degrees, and the rock itself gives off carbon whether your kiln runs on coal or clean electricity. Cement alone accounts for roughly 8% of humanity's carbon emissions. Steel adds another 7 to 9%, most of it from burning coal in blast furnaces. Put those together and you are looking at somewhere near 15% of all the carbon dioxide the human race produces, coming from just 2 materials. That is more than the entire aviation industry. And there was no obvious way out. Slow and clean, or fast and dirty, pick one. For decades, that was the whole menu. Then one country decided to look at a plant everyone had already dismissed and ask a different question. The plant is bamboo, and the first thing to understand is that bamboo is not a tree. It is a grass, the same botanical family as the stuff in your lawn, just scaled up to something that can reach the height of a 4-story building. Because it is a grass, it behaves in ways a tree simply cannot. It is the fastest growing plant on the planet, a title it actually holds in the record books. The vertical record belongs to a species that put on 121 centimeters in a single 24-hour period. Moso bamboo, the workhorse variety China uses for construction, has been clocked growing well over a meter in a day during its spring surge. It does this through a strange trick most plants cannot manage. The cells are already formed inside the shoot before it emerges. Instead of slowly dividing and building new tissue like a tree, bamboo just pumps those pre-made cells full of water and stretches, like a telescope extending. And because it is a grass, cutting a stalk does not kill the plant. The root network underground stays alive and pushes up a fresh stalk on its own. No replanting, no bare hillside, no decades of waiting for the land to be useful again. A structural stalk is ready in roughly 5 to 7 years, and then it comes back, year after year. The strength is where it stops sounding like a gardening fact and starts sounding like an engineering one. On a strength-for-weight basis, the fibers running the length of a bamboo stalk can resist being pulled apart about as well as mild steel. That is not a marketing line. It is why, in cities across Asia, you can still watch workers lash bamboo poles into towering scaffolding and climb it to build glass skyscrapers, trusting their lives to a grass every single day. People have known bamboo was strong for thousands of years, so the obvious question is, if it is this fast, this strong, and this forgiving, why did engineers spend a century refusing to build anything serious with it? The answer is that a raw bamboo stalk, for all its strength, is an engineer's nightmare. It is hollow, which makes joining pieces together awkward. It is round, when every beam and column in modern construction wants to be a flat, square, predictable shape. Drive a bolt through it, and it tends to split lengthwise like kindling. Leave it untreated, and it rots and draws insects, and worst of all, its strength is wildly inconsistent. Two stalks cut from the same clump can perform completely differently, and even a single stalk is stronger near the base than the tip. Now think about how a building actually gets approved. An inspector cannot sign off on a beam because it is probably strong enough. Every structural member has to behave identically every time, in the heat, in the cold, and 30 years down the road. Wild bamboo could never promise that, so the profession gave it a nickname that stuck for a century. The poor man's timber, fine for a hut, never for a city. The breakthrough was not finding a better bamboo. It was refusing to treat bamboo like wood at all. And this is where the family tree of the material splits into two branches worth keeping straight, because almost every popular version of this story blurs them together. The first branch is laminated bamboo. You slice the stalk into thin strips or veneers, dry them, glue them, and stack them into big rectangular beams and panels, exactly the way engineered timber like glubam is made. In China, this is often called glubam, glued laminated bamboo. It is what those 7-story towers and truck bridges are actually built from. The second branch is the more radical one, and it is called bamboo scrimber. Instead of slicing the stalk into neat boards, a machine crushes the whole thing and tears it apart along the grain into a loose, stringy mat of fiber, a step the industry calls fiberizing. What comes out looks less like lumber and more like coarse straw. And that is the entire point. Every weakness bamboo had, the hollow core, the round shape, the splitting, the inconsistency, vanishes, because the original stalk no longer exists. It has been reduced to raw fiber. From there, the fibers get soaked in resin, lined up all in one direction, and pressed under enormous heat and pressure that squeezes out nearly all the trapped air and locks everything into one solid block. Forget the loose pile of sand versus a slab of stone comparison. Picture instead a heap of loose steel wool crushed and fused into a bar you could not dent with a hammer. The finished material is dense enough to sink in water, harder than most hardwood you can buy, and, crucially, uniform. A chaotic natural plant has been turned into a manufactured product an inspector can trust. And it wastes almost nothing, because you are crushing the whole stalk, the crooked pieces, the thin tips, and the low-grade offcuts that a sawmill would throw away all go into the mix. The numbers back it up. High-density bamboo scrimber has tested with tensile strength above 200 megapascals and compressive strength comfortably past 100, with bending strength that lands somewhere between 100 and 200 depending on how hard the block is pressed and which species goes in. That is a grass, one that regrew in under 10 years, performing like premium engineered hardwood and, in some measures, beyond it. Now, for the twist that reframes the whole thing. This is not a discovery from last year. High-strength bamboo scrimber was first made in a laboratory at Nanjing Forestry University in 1987 out of bitter bamboo. The Chinese Academy of Forestry pushed it further in 1989, and by the late 1990s, companies in Zhejiang were producing it industrially. The chemistry has been quietly maturing for close to 4 decades. What changed recently was not the recipe. What changed was the willingness to bet a construction industry on it, and turning that bet into real buildings meant clearing a hurdle that has nothing to do with fibers or resin at all. That hurdle is the building code. A strong material sitting in a lab changes nothing on its own. Plenty of brilliant materials die in the gap between the test rig and the job site, because codes move, slowly, deliberately, on purpose. The cost of getting a structural material wrong is not measured in dollars, it is measured in whether the building stays up. So you need years of testing, agreed standards, and a paper trail any inspector anywhere can pull up and trust. For most of bamboo's history, that trail did not exist, and honestly, even now, there are gaps. When researchers recently mapped the companies making structural bamboo products worldwide, they found that only about 37% published clear data on how strong their products actually were, and only around a quarter held basic environmental certification. If you are an architect staking your license on a material, silence like that is a deal breaker. But that gap is closing fast. Engineered bamboo is now being run through the same international test standards used for structural timber, and the research has exploded. Thousands of studies stacking up in just the last decade, each one another brick of evidence an inspector needs before signing off. And once that confidence arrived, people stopped using engineered bamboo for flooring and started using it for things nobody would have permitted 10 years earlier. The clearest way to see it is to follow one man. His name is Xiao, and he has spent his career shuttling between universities in China and the United States, with posts at the University of Southern California and now Zhejiang University. Back in December of 2007, in the village of Liang in Hunan Province, Xiao's team opened a single-lane road bridge built from prefabricated glued laminated bamboo girders. A crew of just 4 to 8 workers assembled it in about a week with no heavy machinery. It was designed for 8-ton trucks, and when they field-tested it with a 2-axle truck deliberately overloaded to 8.5 tons, it held with room to spare. A bridge made of grass carrying a loaded truck in 2007. That was the proof of concept. The payoff came 17 years later. In early 2024, that same research group topped off the Ninghai Bamboo Tower in Ningbo on the site of an old industrial plot. 7 stories, 6 full floors, and a loft, 20 and a bit meters tall, around 800 square meters of floor space, and built mainly from glued laminated bamboo and cross-laminated bamboo and timber panels tied together with metal connectors. It is recognized as the world's first and tallest engineered bamboo building of its height, and it was designed against real seismic and wind codes not waved through as a novelty. This is the moment the poor man's timber stopped being a joke. Engineered bamboo is now carrying real loads in real structures that real people work and live inside every day. And the country behind it is not treating this like a fun experiment. It is treating it like policy. In 2022, China and the International Bamboo and Rattan Organization jointly launched an initiative with a blunt name, Bamboo as a Substitute for Plastic, formally unveiled that November and tied directly to China's climate commitments. The following year, China rolled out a 3-year national plan to scale bamboo up as a replacement for high-emission materials, complete with demonstration zones meant to prove the industry works at scale. And the scale is the part most people underestimate. China holds roughly 1/5 of the world's bamboo forest, somewhere around 7 million hectares, over 800 species, and it has built the entire supply chain, from the forest to the fiberizing machine to the finished structural beam. The output value of China's bamboo industry climbed from about 82 billion yuan in 2010 to over 500 billion by 2023. And the official targets call for it to pass 700 billion yuan and then break a full trillion by 2035. When a government puts numbers that large on the table, the rest of the world stops watching and starts competing. But before we picture a planet framed entirely in grass, there is an honest part of this story that deserves just as much airtime. And skipping it would be dishonest. That dense, miraculous bamboo scrimber is held together with resin, often a phenolic resin. The resin is what gives it strength and water resistance, but it also means the finished beam is not a pure piece of plant anymore. It is a composite, and composites raise real questions. How does it behave in a fire? How does it hold up across 50 years of humidity cycles? What happens to all that resin when the building is eventually demolished? These are being studied carefully right now, and they are not fully answered. There is also a carbon catch worth naming plainly. Raw bamboo is a fantastic carbon story, but the more you process it, the more of that advantage you spend. The intense heat, the pressing, and the resin loading mean highly engineered scrimmer carries a meaningfully higher embodied carbon footprint than a simple bamboo pole. It is still generally far better than steel or concrete, but made of grass does not automatically mean free of impact, and serious life cycle accounting is essential. Then there is geography, which may be the biggest catch of all. Turning raw stalks into certified structural beams takes factories, fiberizing machines, resin baths, and heavy hydraulic presses. China built that industrial chain over decades. A country blessed with wild bamboo but no industrial base cannot flip a switch and start turning out code-approved beams overnight. And that is the cruel irony. The very places that could benefit most from a cheap, fast-growing building material across the developing tropics are often furthest from the equipment needed to make it. Closing that gap is not really a science problem anymore. It is an investment problem, a training problem, and a policy problem. And as we already covered, building codes move at a crawl by design because safety comes before speed, always. Zoom out, though, and the direction is unmistakable because the technology is already leaking outward the way every real industry eventually does. When researchers cataloged the structural bamboo sector, the center of gravity was clearly China, but new manufacturers are now appearing in the United States, India, Indonesia, Vietnam, and Singapore. South America, home to guadua, one of the strongest bamboo species on Earth, is waking up to it as an export crop. And there is a reason the interest is spreading, and it is not sentiment about plants. It is arithmetic. If you are a builder facing carbon taxes and tightening environmental rules, a structural material that regrows in under a decade and locks carbon inside your building instead of venting it into the sky is not a feel-good choice. It is a competitive edge. In a market where carbon is priced, that edge turns into money, and no serious construction company can ignore money for long. It is worth being clear-eyed here, too. Engineered bamboo is not about to replace all steel and concrete. Skyscraper cores, long-span highway bridges, deep foundations, those remain steel and concrete jobs for the foreseeable future. What bamboo is doing is carving out the mid-rise, the modular, and the fast prefab space, exactly where lower weight and lower emissions matter most. So, step back and look at what actually happened. Engineers took a plant the entire construction world had written off as fit only for scaffolding and huts. They stopped trying to force it to behave like wood. They crushed it into raw fiber or sliced it into strips and pressed it back into something stronger than the hardwood it replaces and stiff enough to satisfy an earthquake code. It regrows in under 10 years with no replanting. It stores carbon while it is standing in a forest, and right now, it is holding up a 7-story tower and carrying trucks across rivers. For thousands of years, building bigger meant cutting down something that took a human lifetime to grow back. For the first time, there is a serious structural material that grows back before a child finishes school. That is genuinely new, and it is genuinely exciting. If this changed the way you look at the chair you were sitting in or the next building you walk into, hit that like button. It really does help this channel keep going. Subscribe and turn on notifications so you never miss a story like this one. And tell me in the comments, if a plant that experts laughed at for 100 years turned out to be this powerful, what else do you think we are overlooking, sitting right in front of us?